Hello friends. In this video I'm going to discuss the concept of sieve methods. So in textbook this is actually chapter 5, sieve methods. So sieve method is nothing but you have to find out the size of a set. Okay, we have to determine the size of a set. We overcount the set. Just that if we overcount the set, then how can you determine the size of the set? So you have to subtract unless the exact size is known. That is the process of sieve. Okay, sieve method. This is the concept of sieve. So when we are going to actually we are going to determine the size of the set, then what is happening? We overcounted the set. And to get the exact size of the set, we have to subtract. Okay, so until we get the exact size of the set. So this is very interesting, and the first classical example is the principle of inclusion exclusion, which you already obtained actually. Principle of inclusion exclusion. So this is the principle of inclusion exclusion, the pictorial representation. So you just see, if two sets are there, finite sets are there, then if I am going to count the elements of A and B, A union B, okay, what we are going to show? We are going to count the element. First we are going to count the element of A, okay, and then we are going to count the element of B. So then we add this. But you can see, when we are going to count the element of A, then this part is counted, and when we are going to count the element of B, then this part is again counted. Okay, so we have to delete this part, delete this part once. So therefore, after counting A and counting B, you have to subtract number of elements in A intersection B. So this is for two sets A union B. Okay, so first you count the element of A and then count the element of B. So this part is counted actually twice. So we have to subtract this intersection part once. Okay, so it is actually clear in case of actually three sets. You just observe, when we are going to count the element of A union B union C, then we first count the element of A, then B, then C. Okay, then you can observe this part is, the red part is counted, the dark red part is counted once for A, once for B, and once for C. Okay, so first we count the element of A, count the element of B, count the element of C, we are going to add. Then since for AB we have counted A intersection B twice, okay, A intersection B twice, so you have to subtract this A intersection B. Okay, so when we are going to subtract this A intersection B, then this part is also actually this part is also deleted. This part is also deleted. Similarly, when we are going to subtract, because for BC we count this part twice. Okay, this part twice. So when we are going to delete this B intersection C, and then this part is again deleted. Similarly, C intersection C, this part is deleted. So that is in this part, in this there is no element. We have not counted the element of A intersection B intersection C. Okay, so since three times we have deleted this, already we have counted this part once in A, this part once in B, this part once in C. But for intersection B, this part is deleted. B intersection C, this part is again deleted. C intersection A, this part is again deleted. So therefore it is actually deleted in three times. Though we have counted this in three times, we have deleted this part in three times. So we have to add this part. Okay, so this is the actually concept, principle of inclusion exclusion. Principle of inclusion exclusion. So next part, if I consider four sets, okay, if I consider the four set, then this is actually, this part is we have to count this four sets, A union B, union C, union D. Then you have to do this part. So this part will be there. Then A intersection B intersection C plus, okay, intersection B intersection D, okay, then B intersection C intersection D, okay, then the A intersection C intersection D, something like that, and you have to delete this A intersection B intersection C intersection D. That is the process actually, principle of inclusion exclusion. Okay, principle of inclusion exclusion. So this is the concept behind the principle of inclusion exclusion. Okay, this is one kind of actually Sieve method. Okay, so now there is a very interesting result in a generalized version. So if these are the actually A1, A2, A and B the subsets of X, I'm going to consider in my copy. Okay, so these are the subsets of say X, A1, A2 up to An. These are the subsets of X. Then we have this result. So we have this result. Okay, we have this is just a number of element, X difference this, then this is just use this part exactly same way. So this is plus minus, again same thing is happening here. We don't know whether this is this one is minus 1 to the power n, whether it is plus or minus, we don't know, and depending upon whether the number of elements in this union, number of element in this number of sets in this union is even or odd, it will determine the minus 1 to the power n, whether it is plus 1 or minus 1. Okay, so now how you can establish this result? Okay, you see this, how you can establish this result. So you see two possibilities are there. Okay, the element in this set or this set of this side and set of that side. Okay, so either X belongs to this union or X does not belong to that union. Okay, so two possibilities are there. So we first consider, say X does not belong to this union. So if X does not belong to this union, okay, so then it is counted once in the either side, because X does not belong to this union means X in this union. Okay, so we are going to count once only, count once that particular element. Okay, this union means we have to delete those elements from here. Okay, which are at least one of this AI. So since that X does not belong to this, at least one of this AI, therefore X does not belong to this set. So X belongs to this here. Okay, so we are going to count actually that X once. Okay, so whether that X is counted once in the right hand side or not, we have to check. Yes, because we are not going to count that X here, because X does not belong to this union. Union means it is not a member of any one of these n sets. Similarly, it is not the member of this intersection, because this X does not belongs to AI for any I. So it is not possible that X belongs to AI intersection AJ. So X does not belongs to here, does not belongs to here, and does not belongs to here. That is, we have counted once that XX for this part only. So here also we have counted once, here also we have counted once. So if X does not belongs to this, then this part is okay. Okay, we are going to count that X here left hand side once and right hand side also once. Okay, so now for the next observation. So the next observation, you can see, suppose X belongs to this. Okay, suppose X belongs to this union, and suppose X is in exactly M of the sets AI. Okay, that is X belongs to this union means X belongs to at least one of these AI. Okay, one of these AI. So one means, say you consider, say X belongs to M sets, say A1, A2 up to AM. So these are the sets, say A1, A2 up to AM. Okay, X belongs to this. So now you see in the left hand side, since X belongs to this, therefore X does not belongs to this part. Okay, so therefore the count on the left hand side is 0 for that X. Okay, the count on the left hand side is 0. Okay, so we have to show that the count on the left hand side or count on the right hand side is also 0. That is, count on the right hand side for that particular X, that is X belongs to union of this AI. Okay, this is also equal to 0. Now see, so here we are going to in this mode of x means we are going to count that x once, that is 1. Okay, so here n sets are there. Out of this n set, m set contains this x. Okay, m set contains this x. Therefore we are going to count that x here m times. So this is nothing but actually m choose 1. This is nothing but m choose 1. So if I choose, okay, from any of these m set, okay, that x, okay, that x, then this will give the total number of actually counting of that x in this collection of ai, that is I from 1 to m. Okay, I from 1 to n, because x is in exactly m set. Okay, okay, x is in exactly m set. Similarly, for here also you can see, if I concentrate on this part, you can see we have these m sets are there. We have these m sets. Okay, these m sets are there. So for the second part, so a1 intersection a2, a1 intersection a2, if because x belongs to this m set, so a1 intersection also belongs to that a1 intersection x also belongs to a1 intersection a2, that is okay. Similarly, x also belongs to a1 intersection a3, a1 intersection a4, a1 intersection a5, okay, a1 intersection am. Okay, x also belongs to a1 a2 intersection a3, a2 intersection a4, something like that. That is, if I choose any two sets, then you will get actually one count for that particular x out of this m set. Okay, if I choose any two members of this m set, then we are going to count that x once. Okay, so in this summation cell, therefore in this summation sign, we count this x in how many ways? In mc2 ways. Okay, for 3 sets, this will be nothing but mc3 ways, something like that. Okay, mc3 ways. So up to this is minus 1 to the power m choose m. Okay, this is the count of x in the right hand side when x belongs to this. But if you remember this result, this is equal to 0, because you see this is a very interesting observation. 1 plus x to the power m, this is 1 plus m choose 1, m choose 1x, 1 plus m choose 2x square, m choose m x to the power m. Replace x equal to minus 1, this part will be 0. So 1 minus m choose 1, m choose 2, m choose m minus 1 to the power m, because x is replaced by minus x. Okay, x is replaced by minus 1. So this is nothing but 0. Okay, so if x belongs to this, then we have the count for x in this part is 0. Similarly for that part, so this will give the required result. Okay, it will give the required result. So I will discuss the later part. Thank you.